Hi everyone, my name is Zijian Wang. In this presentation, we will walk through the prototype matching graph network for heterogeneous domain adaptation. Domain adaptation focuses on the knowledge transfer from the label-rich source domain to the label-scarce target domain. While the previous domain adaptation limited to the knowledge transfer between the same type of feature, heterogeneous domain adaptation is proposed, which aims to facilitate the knowledge transfer among the different types of feature from various modalities. Previous heterogeneous domain adaptation methods focus on training adaptable classifier, aligning cross-domain manifolds, minimizing the domain discrepancy by applying maximum mean discrepancy. But they are all limited in a sense that they do not explicitly maximize the margin among different classes of the target domain. For example, we can see that the marginal sample may be misclassified in this case, where our method is trying to achieve the largest margin among different classes by forming tight clusters for each class. Now I would like to present the methodology part of our work. So this is the overall framework of the prototype matching graph network. The network consists of three parts, which is graph learning module, the shared subspace clustering, and the swap training strategy. We'll start with the graph learning module. The graph learning module aims to close the gap between the node representations and their corresponding class prototypes across the domains. So in here, we jointly consider three different losses. So one is the discrepancy loss, age prediction loss, and the node prediction loss. So for the discrepancy loss, we employ the maximum mean discrepancy to minimize the discrepancy between the source domain and target domain. Well, the age prediction loss is using the binary cross entropy of the ground truth age map and the predicted age map. And the node prediction loss is for the label prediction. The second component is the shared subspace clustering module. Since one of the key factors is to ensure the effective graph learning, is that the node representation of the initial input graph should reflect the semantic correlation of the original space. The subspace clustering module aims to obtain the tighter cross-domain clusters for each class. We're using the KL-divergence to measure the distribution difference of the cluster assignment probability distribution Q and the target distribution P. The third component is the swap training strategy. Since the available label sample in the target domain is very limited, we are employing a swap training strategy, which gradually includes the pseudo-label target sample in the training process, while dynamically adjusting the number of labeled target samples. At the AMPS training step, we construct the pseudo-label set D PM. And for each mini batch of the AMPS training step, we are using those rules to select sample. To demonstrate the performance of the proposed method, we conducted the experiments on three different heterogeneous domain adaptation tasks, which are the object recognition, text categorization, and text image classification. Well, the first tasks, we are having the different feature types, and second task, we are having the different feature dimensionalities, and the third one, we have the source and target domain from the different modalities. So this is the result of the task 1. And that's the result of task 2 and 3. We can see that our method can achieve the highest average accuracy. And we refer the audience to the paper for detailed result analysis. And this is the feature visualization. So we can clearly see that the tighter clusters with a good class-wise mix of the source and target over the baseline methods, which strongly demonstrate that the idea of domain-invariant class prototypes. So thanks for your attention, and the source code will be available at the GitHub, and feel free to contact me at this email address. Thank you.